morning. Okay, so the last day we talked about the ideal gas law and we derived it using Boyle's, Charles and Gay-Lussac's law. And we also defined the temperature known as the Kelvin scale coming from Charles' law. Okay, so today we're going to say more about the quantities in the ideal gas law. We'll also write a different form of it. So we had the following. And we had this N. N is the amount of gas, poorly defined. However, we'll look more closely at this N right now. N will be the number of moles, which is a unit of measurement of a gas in terms of particles. Now we were actually studying the ideal gas law in terms of the fluid as perceived by the people, the philosophers of the 18th century, but in the 19th century it became apparent that a gas was made up of particles, which later became molecules. Let's look at all the quantities in here first. P, pressure, which is force over area, which is newtons per square meter, and these guys are called pascals. Pascals are our units of pressure in terms of SI units, newtons, and cubic meters. Sorry, square meters is area, cubic meters is volume. Since we're talking about volume, let's look at something else. The quantity PV is force over area times height. Volume could be the height of a disk of area A pi r squared, h, but let's say h is dx instead, delta x. The areas cancel and we get 4F, force, times delta x, or force times displacement, which is work. Work done, or work done by. Strictly Newton meters are the units of work, but they're the same as joules. It's equal to the energy expended. So the other quantities in here are the following. R is the universal gas constant. T is temperature. Now we know it's in Kelvin. We don't write degrees Kelvin like that, we just write K. For example, that's just a reminder, 273 K is the same as 0. It's actually the same as 0 degrees centigrade. So we have P, V. V of course is volume in meters cubed. Now, when we use what we're going to call moles for this amount of gas, we could have it in kilograms actually. But if we use moles, then this universal gas constant has a value of 8.314 approximately joules per mole per Kelvin. So these are all the things in the ideal gas law. And we're going to look at this N. N is the number of moles of gas in a system. Our system consisted of a cylinder and a piston, which was free to move depending on the change of the volume, the pressure, or the temperature of our gas. No particles can get in and out of the system. Now it could be Suppose n was 12 particles. N is a number, right? It's actually a number. If n was 12 particles and we had, let's say, 72 particles in the container, we could say the following. I didn't mean it exactly like that. For n equals 1, we'll say 12 particles. Okay, so there are 6 dozen particles in this system. If there were 144 particles in our box, we would say there are 12 dozen particles in the box. If there were 42 particles in our box, we could say that there were 3.5 dozen particles in the box. Okay? But n is not that. N is a different number. Now, n is a number of particles, so the units, it doesn't have joules in there, it doesn't have kilograms in there, it's a number of particles. It has a special reason for being that number, and I'll give you this reason in a minute. If, for example, there were 12.4 by 10 to the power of 23 particles in our box, we will say that n equals 2. Or we have 2 moles of particles in the box. Question. If there were, let's say, 48.16 by 10 to the power of 23 particles in the box, n would be what? Question? 4. 46.16, it's, sorry, 48.46 If there were that many particles in the box, we would say n equals 4. So you see n is just a counting number. But it has this value for a very specific reason. This value here is given a name. It's called after the man I have already mentioned. Character number 5, Avogadro. When n equals 1, when n equals 1, in other words, we have 1 mole of particles in the box, we say we have 6.02 by 10 to the power of 23 particles in that box. Na is Avogadro's number. And it has a very special reason for having that value. We'll look into that reason now. Why is Avogadro's number the number that we use? Why is it this value? Now, Avogadro's number, 6.02 by 10 to the power of 23 particles, cannot be worked out. It can only be found experimentally. And there are various tricks and means to find that number. When you find that number, you can find the mass of the hydrogen atom. You can find the mass of a proton, approximately. You can find the mass of a helium nucleus or an alpha particle. So we're looking at Avogadro's number. Amedeo Avogadro was Italian. n subscript a will always be there to denote Avogadro's number. Why is it this value? Well, here's the answer. The answer lies in what's called the gram atomic weight or the gram molecular weight. We look at these two ideas. Gram is an arbitrary amount of matter. If we were choosing the pound or the kilogram atomic weight, n would have a different value. If we were using an ounce, n would have a different value. We could use an ounce, avoirdupois. We could use all sorts of units, but we're using grams. I'm sorry they didn't define it in terms of kilograms, in which case if it was kilograms, this would be 26. But it's not, we're using grams. All right, so why does Avogadro's number have that value? And the answer lies in the gram molecular weight. Now, hydrogen, atomic hydrogen, the hydrogen atom has atomic weight of 1. Actually, because of the existence of different isotopes, it's really 1.0008. But we're going to round it off. We'll always deal with the rounded off atomic weight. Helium is atomic weight 4 and atomic number 2. Has 2 protons and 2 electrons. Sorry, 2 neutrons. And the mass of the neutron and the proton are approximately the same. We'll say that they are both 1 atomic mass unit. So that's 4 atomic mass units. 1 atomic mass units. Now we look at oxygen and carbon. The atomic weight of this guy is 16. So 16 is the atomic weight for this guy. Carbon 12. We use carbon 12 for dating sometimes, it might be wrong. It'd be interesting if carbon dating was wrong. The dinosaurs might have been much more recent. Not sure about that. Okay, so the gram molecular weight, this guy, of hydrogen is 1. In other words, the atomic weight is written in grams. The gram molecular weight of helium is 4 grams. The gram molecular weight of oxygen the gram molecular weight of carbon is 12. Therefore, what is the gram molecular weight of atomic uranium? Answer, 238 grams. Now here's what the idea of Avogadro's number is. If this is 1 gram, this is 4 times the weight of it. Look, 1 proton, 4 of them. This guy here, 16 nucleons in there. This guy here, 12 nucleons. 12 times this one. 4 times 1, 16 times 1, 12 times 1. 1 is fundamental. Okay, here's what Avogadro's number is. This is a statement. Write it down. People go through chemistry without knowing this. I'm not a chemist, but I could be. The reason is, one of the things I studied is quantum mechanics, and quantum mechanics explains all of chemistry, so therefore I could be a chemist. Chemists wouldn't like that. Chemists deserve respect. Don't worry, I don't know how to manipulate all the pieces of equipment that they have. Avogadro's number Na is If you ever have a teacher, always get a statement out of them. The equivalence principle. People talk around it, but they don't say exactly what it is. Avogadro's number is. Here is the answer. I'm using the word make, I mean have or to exist. Avogadro's number is the number of particles needed to make the gram molecular weight of a substance. Or atomic, I'll use these interchangeably. Alright, so let's look at helium. I write helium because we can have atomic helium in a box. Hydrogen gas is H2. Oxygen gas is O2. We don't have those existing as atomic in a box. So, sorry. .02 by 10 to the power of 23 helium atoms has a mass of 4 grams. Or Avogadro's number, Na, atoms of helium has a mass of 4 grams. You can also get atomic carbon existing. Therefore, I'll say it the other way. 12 grams of C12,6 consists of 6.02 by 10 to the power of 23 atoms. And that makes sense. That's 12 times, each atom is 12 times the mass of one hydrogen atom. So therefore, if we had hydrogen as atomic, (6 by 10 to the power of 23 atoms of hydrogen has a mass of 12 grams. What does that tell us? It tells us something very interesting. We can do this for every atom, but it doesn't matter. We'll just do it for hydrogen so that you can see something quite interesting. Hydrogen really consists only of a proton and an electron. And you need 1,830 electrons to make the mass of a proton. So this is really just, if that was H, we have that many atoms, weighs a gram. These two guys are interchangeable. It's really only a proton we're talking about. So therefore then the mass of the proton is 1 gram over 6.02 times 10 to the power of 23. Now a gram is 10 to the power of minus 3 kilograms. So therefore, bring the 23 upstairs and becomes negative. So therefore then the mass of a proton is 1 over 6, approximately 1/6 by 10 to the power of 26 kilograms. And let me get that right. Okay, now we got it. 1.67 by 10 to the power of minus 27 kilograms is the mass of a proton. I'm not sure if I got that right. You can go and check it, but that's how you get it. Let's look at some other examples. Actually, I'll leave the examples for later. I want to define something different now. I want to write Avogadro's number and another constant. We'll relate them. We'll define a new constant, Kb, in terms of two other constants. We'll just simply take the universal gas constant R and divide it by Avogadro's number. And we will take Avogadro's number and divide that in. And it's basically 6.02 by 10 to the power of 23 moles per particle. Now we're okay, let's see. Particles per mole, sorry. So, dividing them in, bring the 23 upstairs and we change the sign. And all together here we have joules over moles per kilogram, per Kelvin, times moles per particle. Sorry. And we get, what do we get? The moles cancel, and we get joules per Kelvin per kilogram. Joules per degrees Kelvin. This is called Boltzmann's constant. It plays a huge part in physics, along with it's up there with the gravitational constant, the mass of an electron, the charge on an electron, the fine structure constant. Well, not quite, but it's in there. It plays a great role in statistical physics. Boltzmann's constant we'll denote by Kb. Should be a small k, but it's okay, I'm not right. Right, define a new constant Kb. Now let's see. So therefore then, we can write R, using this, equals Na times Kb. So therefore we can take our our ideal gas law and substitute in for R. Now look at this quantity here. So that's 3, for example, and we know what this is. Then 3 times this is the number of particles in the system. N times Na is the number of moles times the number of particles per mole, which is the total number of particles. So therefore, N times Na is the number of particles in our system, so we can write PV. We're going to call this an NU number, N with no subscript. And now we have a very beautiful and elegant form of writing the ideal gas law. Now remember we said the quantity PV as units of energy. This is just a number. Now this is the number of joules per particle per Kelvin. Per particle. So therefore then, joules is just the total number, as the t's cancel, the total number of joules in the system. And we write in the joules per Kelvin, per particle. So therefore then, all along we've been playing with this guy here as just being the total energy in the system. And it's amazing, right? PV equals NKT. I have more to say on this, but I'll leave it for the next class. And then we'll start doing some examples, okay? And then you'll get used to the way I talk and the way I think. I want you to think along my lines of thought. One step at a time, and don't leave anything unturned. If you find that I've forgotten to explain something, then you got to write in and tell me. Because I try to cover everything pedagogically. So that's it.